First of all, I would like to thank the organizer for giving me this opportunity to speak. So I'm also going to talk about the first, but maybe question from the previous.
Speak a little louder.
Okay. So
Also, the microphone is in the middle of the room, so Alex maybe hears better.
so I should stand it. Okay. Okay. So let's look at this equation. Okay. So and we know that from this Fermat last film, people are interested in looking for integer solution for this equation xn plus yn equal to zn, and we know that when n greater than or equal to 3, there's no integer solution. Okay. So you may also ask a similar question for functions. For example, you look for solution of this equation when x, y, z, they are entire functions. Now you may go back to this equation and then divide both hand side by z. Then you will have a functional equation of this form: fn plus gn equal to 1. And this time you may allow yourself to consider holomorphic function f and g. Okay. And so in 1939, already we know that this functional equation has no non-constant entire solution when n greater than 2. And when n is equal to 2, then you can actually solve it. So all the solution would be given by basically cosine and also psi together with some non-constant entire function alpha. And then if you look for holomorphic solutions, okay, so Gauss also solve this equation when f and g, they are holomorphic. And the solution are given here. So this is in this form. So basically a rational function in some holomorphic function. Okay. So that's for the case when n is equal to 2. Okay. And when n is greater than 3, again, there's no non-constant holomorphic solution. So now if you let n to be 3, then Baker, he also found explicitly all the holomorphic solution. So they would be given by certain elliptic function of this form. Okay. So capital F and capital G would be these two elliptic functions. So the next problem you may consider is now you add one more term. So you consider this 3-term Fermat functional equation, fn plus gn plus hn equal to 1. Okay. And then you can consider 4 classes of solutions. So it's either holomorphic, rational, entire, or polynomial. Okay. So obviously you can find some solution for this functional equation. For example, you would take the first coordinate to be f, and then the second one g to be omega 1 multiplied by f, and the last one is actually a constant omega 2. Okay, and so this omega I, they satisfy these 2 equations here. Okay, omega 1 to power n is equal to -1, and then omega 2 power n is equal to 1. Okay, so this one will be a solution for this equation, but we will classify them as trivial solution. Okay, so we would like to look for non-trivial solution for this functional equation. Okay. So here is a table of all the known results so far. Okay. So now for each class, if you take n sufficiently big, then there's no non-trivial solution. Okay. And so people also construct non-trivial solution when n are small, and I'm going to show you some of them. Okay, so the last column would be the unknown cases. So for each class, and So I think Walter Heyman in 1985, he applied advanced theory of the vanilla theory to study these kind of problems. Okay, so he also studied a related walling problems as well. Okay. However, before Walter Heyman, actually, Total and Fujimoto, they also consider this a functional equation, actually more general. They also consider the case when this degree, they are not equal. Okay. So, and then there are other people who try to construct explicit solution. Okay. So here would be some example for the explicit solution. So when n equal to 1, then you can take this one. And then this is 2 and 3. So here alpha is a anti-function, non-constant anti-function. So I'm showing you the entire solution, okay? Because this talk would be mainly about entire solution. Now for n equals to 4, you have something more complicated. It's given by either this set, FGH in this form, and it was constructed by force. Or Mark Green also get another set of solution, which is given here. And when n is equal to 5, 20 years ago, Gunderson and Toji, they construct this solution. Okay. So it's highly non-trivial to construct explicit solution. Okay, so this is n equal to 5. Okay, and we will come back to this set of solution later on. And then for homomorphic solution, I'm not going to show you the explicit form of them, but I just want to mention when n equal to 6 and 5, you can also construct explicit homomorphic solution. And often they are in terms of elliptic function. So here would be a list of open problem if we focus on basically transcendental homomorphic and entire solution. So for entire solution, the only open case would be n equal to 6. And that's why in today's lecture, we will focus on this case. And then for homomorphic, it would be n equal to 7 and 8. So, so this problem have been studied by quite a number of people. I just mentioned a few reference here. For entire solution, when n is equal to 6, total in a old paper, actually, if you apply his result, you can prove that you cannot find non-trivial solution if one of these function FGH has no zeros. And then there's another interesting case. If you assume FGH, all of them so should be strict order strictly less than 1, then the solution has to be trivial. Now I'm going to again study this problem, but this time in terms of some geometric terminology. So I will consider the so-called Fermat surface, which I'm going to denote it by Mn, and it will be given by this equation 4 here. Okay, and I'm looking for points in the projective space, P3. Okay. And so for entire solution, okay, so you can think of each set of entire solution FGH as a mapping from C to P3, given by this formula here. So 1 F, G, and H. So now I want to recall the definition of a Brody curve. Okay, so it's a little bit different from what we have seen before. So let's look at a map F from C to Pn. Okay, and we represent it in this reduced representation, which means all the coordinates, they don't have common zeros. Now I'm going to use this law, the Euclidean law, and then define the Fubini-Study derivative of the map F, given by this expression here. Okay. And then So F is a Brody curve by definition if this is a spherical derivative or it is bounded over C. So what I'm trying to prove for today's lecture would be this result. So you cannot find a non-trivial Brody curve on Fermat surface of a degree 6 of this form. So F, G, H, they are entire holomorphic function. Okay. By the way, this is a joint work with Psyche Yang, also a colleague of Alex from Brody. So
Wait, so by the Brody lemma, doesn't that mean there's no entire solutions?
what do you mean?
I mean, the Fermat surface is compact, so Brody's lemma applies, right? So if there was an entire solution, you could rescale to get
No,
a
so
Brody.
we are looking for non-trivial. So it has solution actually. It has trivial solution.
It is a Brody curve minus line. It's not compact.
Because there's lines.
Yeah.
He considers entire solution, so it's
Yeah,
not compact.
There's lines, yeah, okay.
So thank you. Now, so the proof will consist of mainly two parts. Okay. So the first part, I'm going to apply a version of a Whitman-Wright for vector value entire function. Okay. And so I'm going to prove that there's no entire non-trivial solution as long as each coordinate function FGH, their order is strictly less than this number, 119 over 117, just greater than 1. Okay. And then the second part of the proof would be basically using a result of Alexander Eremenko, okay, on Brody curve opening hyperplanes. Okay. So this is the statement I'm going to prove using this result of Alex. So if you let capital F to be of this form, so the coordinate function, I change it to F1, F2, F3. Okay. And assume it is a Brody curve. Okay. And lying on the Fermat surface of a degree 6. And each Fi is entire. Okay. And then if you assume this F is non-trivial, okay, then the order of each of these coordinate function would be less than or equal to 1. Okay. And then we combine this two statement. So you will be able to deduce that this result here. Okay. So there's no non-trivial Brody curve on Fermat surface of degree 6. So that's the strategies of proving the main theorem. Okay, so this part. So I'm going to explain to you each of them. So first of all, I need to mention this vector value entire function Whitman-Wright theory, which is not that well known. Now let's consider this vector G. Okay, consists of n entire function, and we can look at the power series expansion for each entire function, and then you write it as this form. Okay, so each coefficient is actually a vector in Cn. And then we have the usual terminology when we only have one coordinate function. So here I'm going to introduce something called maximum term denoted by mu, and it would be given by this maximum here. So now I'm going to consider this norm of AK, and in this part, when you see the norm is always the maximum Cn. Okay, and then you have R to power K. Okay, so fix R, and then you compute this number, and then you try to get the maximum. Okay, and that would be your mu R. Okay. And then so among all this term which attain the maximum, okay, you try to get the largest index m here. Okay, And so this index M will be denoted by this notation here. So that's our notation. And finally, I also need to define this maximum modus function for this G. Okay, it would be given by this maximum here over the circle with center at the origin and radius r. Okay. So so here is the statement for this vector value Riemann-Weintraub theory. Okay, so again we have this vector value function G. Okay, and let's assume it to be a transcendental, which means at least one of these coordinate function is a transcendental. Okay, and then let delta to be a number between 0 and 1/4. Okay. And sorry. So let's look at a circle with radius r, center at the origin. Okay, and suppose you have a point z. Okay, so that this norm here is greater than the maximum of G, the maximum modus function, multiplied with this factor. Okay, so essentially it's slightly bigger than this maximum modus function. Okay, so in general, if you pick any set, this number will be less than this one, but now you multiply with a factor here, so that this thing can be greater than the right-hand side. Now we focus on such point set with this condition satisfied. Okay. And then we have the following result. Okay, so basically it says the following. So this is our G. Okay, and then we can take the derivative of each coordinate. Okay, and you can actually sort of approximate the original G by multiplying the derivative with this factor. Okay, and so there's an error term which is given by this function here, this central index function. Okay. Now for us, for application, you can deduce from this inequality 8 the following information. Okay, so basically it says the following. So you take the derivative, mth derivative, and then you compare with the original function, and then the difference is given by this factor here. Okay. So if you take G to be a polynomial, sufficiently high degree, and then you can take the derivative, and then you will get this kind of things, and get a sense why you get this identity here. Okay. Now in the form that we are going to use, it's actually better to write things in this way. Okay. So now you can deduce from the previous result for each coordinate function. You can also approximate the original function by the higher order derivative. Okay, and so here there's a error term here. Okay, and the good thing about it is now you have a sort of uniform bound about this error term in terms of the norm of the original G. So now if you apply the Riemann-Weintraub, the original version, you also get this kind of approximation. Okay? But each error term would be unrelated. Okay? But here, using this version, so you have some control on the error term in terms of the norm of G. So yeah, I'm going to prove this proposition 1. Okay, so I just mentioned that so there's a result by Li and Su. They prove the same result, except their order is strictly less than 1. Okay, later on you will see it's important to have something just greater than or equal to 1. Okay, so okay, now how to prove this proposition? So we start with our original equation. So I rewrite it in this way. Okay, and then I can differentiate. Once you get this one, I'm using the differential notation. Okay, but you can also think of them as a derivative. And then I take the derivative one more times. I get this one. So the capital D here would be given by this jet differential. And then you do some linear algebra on this system of equation. Okay, And then you can find out some relationship among all these things. Okay. If you think of them, this derivative or differential as coefficient, so you get this system of equations here. And so all of them are equal. So let's just define it to be a phi here, which is going to be quite important for us. And there's some simple algebraic relationship among these things. And for example, this phi, okay, you can write it as x, y, z multiplied with another z differential, which is given here. Okay, or you will have the original expression here for phi. Okay. And we are going to use this relationship later on. Okay. Now, so the following lemma tells you when you can get a trivial solution. Okay, so one condition would be the following. So if you take your phi multiplied with x, y, z, and then pull back by this capital F, okay, it simply means that you substitute x, y, z by f, g, h, etc. Okay, and suppose this function is constantly equal to 0. Okay, then and I'm going to call this a function p. Okay, so the conclusion would be f, g, h would be a trivial solution. Okay, which means that one of them would be basically a constant. The other two, they are related by a multiple. Okay. Now, how to see this? Okay, so let's assume we have this equation. Okay, but then we also know that our phi is given by one of these things. Okay, and so we can basically check that. So if the image FC is lying in one of these coordinate plane, then we will get trivial solution, and otherwise we will have this one equal to 0. So starting from this original equation, using this algebraic identity, you get this equation, differential equation. Okay. And I can write it explicitly in terms of FGH. It would be given by the first line here. Okay. But fortunately, this equation actually can be integrated. Okay, so you do some careful arrangement, and then you can actually integrate these things. So eventually you will get to this point. So f and g, they are related this way. Okay, and k1, k2, they are constant. So now we know that we have a FGH satisfying the Fermat functional equation. And if you assume our p is equal to 0, then f and g would be satisfied or related this way. So it's actually a parametrization of an algebraic curve. And however, this n in our case is 6. Okay, so the algebraic curve is actually hyperbolic. Okay, and therefore you cannot have an entire map into this hyperbolic curve. So you get FG, they are constant.
So this page is basically what prevents you from deforming away from the Fermat surface, right?
Exactly. So this pair would be the how to get that? Okay, so this pair actually will give you the trivial solution, essentially. Okay. So yeah, so if sorry. Okay, so if we assume K2 they are non-zero, then you will get some non-trivial algebraic curve, and then f and g they are constant. Okay, so therefore you have a K1, K2 to be equal to 0. Okay, and in this case, then you can deduce that the solution you are considering would be a trivial solution given by this expression here. Okay, so let me just recall this useful fact. Okay, so as long as the p is equal to 0, you get trivial solution. Okay, so later on we will try to prove in different situations that this p has to be equal to 0. Okay, now we try to prove proposition 1, which says that FGH, they satisfy this Fermat functional equation of degree 6. And let's assume FGH, all of them have order less than or equal to that number, slightly greater than 1. Okay, and of course FGH, they are entire function. Okay. So we want to prove that in this situation, this P has to be equal to 0. Okay, so that's something we want to prove, and the phi would be given by this jet differential here. Now I need to use a fact from a paper of Ishizaki, which says the following. So if you have a entire curve lying inside the Fermat surface of degree 6, and you assume this is non-zero, okay, not constantly equal to 0. We call that if this pullback of mxyz by f is constantly equal to 0, this is the same as p equal to 0. Okay, so let's assume this is not the case. Okay, and FGH, they will have the same linear characteristic function, basically, up to an over term. Okay, now another useful fact would be this one. So this p under this assumption is actually so in his paper he proved that this is a small function. Okay, however, if you assume FGH, they are of finite order, then this p is actually a polynomial. Okay, so that's another useful thing to know. So the proof would be based on this vector value Riemann-Malin theory. Okay, so I'm going to rewrite FGH to power 6 as G1, G2, G3, and then try to apply this Riemann-Malin theory to this vector value. Okay. So first of all, because we only have 3 functions here, okay, so you can get a countable, uncountable set S. Okay, so that basically if you take any complex number with absolute value R, okay, inside this uncountable set. So, sorry, this is a typo, should be S. Okay, and then we may assume the size of W of each function will be given in this order. Okay, so G1 has the highest, largest absolute value, and so on, okay? And is attained for this maximum value function. Okay. Now, on the other hand, we also have this functional equation satisfied. So those GI you add together is equal to 1, and you just compute the maximum modus function for G and apply the triangle inequality. So you will get these simple things here. Okay, and you take out sufficiently big, so you will get G2 at W will be greater than or equal to 1/3 maximum modus function for G1. So essentially, what it means is okay, so these 2 things, they are not so they are comparable. Okay, so which will give you some control later on. Okay, so now we apply that vector value Riemann-Malin theory. Okay, so the nth derivative would be given by GI multiplied with this factor here. Okay, and the error term, there's a control here. Okay, uniform control. And according to our choice of W, so this norm here is just G1. Okay, and so if we divide everything here by GI, okay, so so this little IM, they will satisfy this estimation here. So finally, we can rewrite the previous estimation in this way. Okay. So that now each of these error term here would be bounded by the same factor here. Okay, so now we are ready to apply this Riemann-Malin theory. So from the definition of P, okay, actually we can do some algebra and find out that they satisfy this differential equation. Okay. And by permutation, you also get another 2 set of similar differential equations. Okay, now you see you have some higher order derivative of GI. So what you need to do is you just replace this higher order derivative of GI by GI itself. Okay, so you will get to this point here. Okay, and then you can do some cancellation and rearrangement. So finally, you will get this estimate. Okay, so I'm only using one equation here to get this equation 21. Okay, but if I do some permutation on these things, I will get two other set of equations. Okay. And also two other estimations here. Okay, so I put all these things together. So eventually, I will get this P, okay, which is bounded above by some Rn to power C, and C would be a negative number if we assume the order of FGH is less than this number. Okay. However, because we know in this particular case, when FGH they are finite and high function, so this P has to be a polynomial. Okay, and therefore you have a infinite sequence, so that this goes to 0. Okay, and therefore this P has to be constantly equal to 0. Okay. So once this P is constantly equal to 0, then you know that F and G will only give you a trivial solution. So that finished the proof of proposition 1. Okay, so any question so far? Okay. So now we are going to prove the second proposition. Okay. So so this is the same. Okay. So if you are basically it says the following: if you assume F here is non-trivial, okay, then the order has to be less than or equal to 1. Now, in order to prove this proposition, we need to use the following observation. Now, you take a Brody curve on a Fermat surface of degree 6, and then you project this to P2. Okay. For example, you just take 2 of this coordinate function Fi. And the conclusion would be this new map would also be a Brody curve. So in general, you don't have this result, but if you assume the Brody curve is lying on the Fermat surface of degree 6, you will have this one. Okay. And then the next result would be the following. So if you assume the spherical derivative is bounded above not by a constant, but by a sort of in terms of a polynomial growth, and then for this projection, you also have the same kind of estimate for the spherical derivative. Okay. So the next lemma says the following. Again, so we are looking at Brody curve on Fermat surface of degree 6. Okay. Now, so this lemma says that there exists some positive constant C. Okay, so that whenever you have a complex number W, so that the absolute value of the first coordinate F1 here is equal to 1. Okay. Then the spherical derivative of the other 2 coordinates would be bounded above by this same C. So these are 2 lemmas that we are going to use. Now finally, we need to use the following result of Alexander Everbank. Okay. So let's look at entire function. So we have n plus 1 of them, and then you put them in this form. Okay, and from now on we will denote ui to be the log of absolute value of fi. Okay. So suppose for the first coordinate function f log, okay, has a 0 at a. Okay. And then we let any complex number to be inside C, so that the absolute value of this complex number is greater than absolute value of a. Okay. And at the same time, when you compare u naught, okay, which is log f log, and suppose this number is greater than the maximum of the log of the other coordinate function. So in other words, this maximum evaluated at this concept is bounded above by u log. Okay. So his conclusion for this result is the following. So if you let so fix this set, okay, and then now you choose the largest ball of radius r, okay, so that you have this inequality satisfied with a ball as center as z and radius r. So you start with this point, okay, and then you look at a ball with center as z, so that any point inside this ball, you also have this inequality, okay, and then you take r to be the largest radius. So and from here you can see on the, sorry, there should be a boundary B here. So on the boundary of this ball, okay, you can find Z1 so that this value is exactly equal to the maximum here. Okay. So now for this particular point here, this boundary point here, okay, so you have the inequality in reverse direction. So now you can have this U0 set bounded above by the maximum. Okay. However, you need to add some extra term here, which is given by the spherical derivative of f evaluated at Z1. And with a factor here. So the factor is 4n plus 1, and then multiply with this capital R. Okay? And this capital R is this largest ball, the radius of this largest ball. Okay? And it has this estimate. It's less than or equal to 2 Z. Okay? So this is the a powerful result. You will see how to make use of it later on. So Alex, make use of this result to prove the following theorem. So you take a Brody curve and omit n hyperplanes in general position. Okay, and then he proved that the characteristic function of f is actually given by OR. So in order to prove this proposition, this one. Okay, so we are going to kind of use some inductive argument. Okay. So we are going to divide the proof in the following step. Okay. So first of all, we want to prove that so if our curve is a Brody curve, okay, and suppose it is non-trivial, then the order of this Brody curve would be strictly less than 5 over 3. Okay, so that's step 1. And then the second step looks very similar. So you assume you start with a Brody curve of order less than 5 over 3, and then you prove that the order actually has to be 4 over 3. Okay. And finally, you assume you start with a Brody curve with this order 4 over 3, and then eventually you prove that the order has to be less than or equal to 1. Okay. So now in the first step here, so you assume the curve is a Brody curve, and this is a well-known fact that for Brody curve the order is less than or equal to 2. Okay, so you start from 2 and then you get 5 over 3, and then from 5 over 3 you get 4 over 3, and so on. Okay, so that's the strategy for proving it. Okay, so now we want to prove the order is less than 5 over 3. Okay, so this is the same as proving all this UI. You have this estimate here, this growth estimate for UI. Okay, so so we are going to prove this in this way. Okay, so let us define A to be the set of points so that this is not satisfied. Okay, so you take the maximum of uj, and then it's greater than this number here, this order of growth here. Okay, now we are going to prove the following. So our goal is actually try to prove this A is bounded. Okay, so if this A is bounded, then you get this things for set sufficiently big. Okay. So we are going to assume, suppose A is unbounded, okay, and try to prove that the Brody curve is trivial. So we are going to make use of elemental theorem. Okay. So we start with Fij defined this way. So we only consider two coordinate functions, Fi and Fj, and I and j are not equal. Okay. And then we apply elemental theorem for this particular case. So you will get this inequality. Okay. So why you have a 0 here? Because you take a log of 1 here, so you get 0 here. Okay. And then you have this supremum of the spherical derivative of Fij. Okay. And this is true for each I. Okay. And then, however, we know that if our capital F is a Brody curve, then this Fij will also be a Brody curve. Okay. Which means the spherical derivative here is actually bounded for each I. Okay. And therefore, we can choose some big number, C log given here, and then we get this inequality here. Okay. So far, okay. Okay. So and therefore you have this inequality. Okay. Okay. Now we assume our A is unbounded. Okay. And therefore if you take A away a ball with a radius R, okay, it will be a long empty. So you can find a point inside here. Okay. And for this point, okay, so any point in this set, we are going to prove that all the UI would be positive. Okay. And we may assume just U1 is less than equal to U2 and so on at this point. Okay. Now suppose U1 is negative at this point. Okay. And then we apply 26. Okay. So you take this is U1 and then this is U3. So you get this one here. Okay. However, we know that our set here is chosen from A. Okay. And so this function here, the functional value, would be greater than absolute value set to power 5/3 minus something. Okay. And therefore you get a contradiction. Okay. And therefore U1 has to be positive. But U1 is the smallest one. Okay. And therefore all this UI would be positive. Okay. So all the UI will be positive at the point set. Okay. Now on the other hand, so each Fi will have at least one zero. Okay, because if they don't have zeros, for one of them, then have been already taken care by a result of a total. Okay, so now if we let a zero of Fi to be Bi, then this UI evaluated at Bi would be less than 0. Okay, so again, you can find a ball with center as set. Okay, so that within this ball you have UI greater than 0. Okay, and at the boundary you will have UI exactly equal to 0 of this ball. Okay, so each radius of this ball will be denoted by Ri. Okay, and then you let R to be the maximum of this radius. Okay, and you also assume those radius are in this order. And then we divide the proof into two cases. So one is this capital R is less than or equal to this factor here, or greater than this factor. So again, we apply Riemann-Roch result. Okay, now this time to this function only. Okay, again, you have 1 here. So when you take log, you get 0. So you only have this term here. Okay. So you also have this spherical derivative of this Gj here. Okay, and then the points would be a boundary point on this 4. Okay. Now, so at this particular point set 1, okay, let's assume the maximum of this one, okay, is obtained by this index J set 1. Okay, And in fact, this JZ1 has to be equal to 2 or 3. So and if you have U1 Z1 equal to 0, okay, this is the same as saying that F1 Z1 absolute value is equal to 1. Okay, and then from one of the previous lemma, okay, we know the spherical derivative that's an upper bound given by C. Okay, so now you put this information into this inequality. Okay, so you get this UJZ would be bounded about by HCR. But then sorry, we call that this capital R. Okay, so in our subcase 1 is given by here, this one. And therefore, again, we apply Evan-Mankel's result to this map. You have another set of inequalities, but this time, this maximum here, you get this estimate here. Okay, and this is the dominant term for set sufficiently big. So you have this things. Okay. So you have U1 less than or equal to this thing. Okay, so notice that this is minus 2 epsilon. Okay. However, your set is taken from A. Okay. Which means this one is greater than this number, and therefore you get a contradiction. Okay? And therefore, for the first case, if you have the assumption that A is unbounded, then you have a contradiction. Okay, so first case will not happen. Okay? So the second case would be this one. So this capital R is greater than this number. Okay, and so what we are going to do would be the following. So we are going to again to estimate our P under this assumption. Okay. So you can rewrite this P in this form. Okay, in our notation here. So F16 is given by capital F1 and so on. Okay, so and then we can also assume some ordering. Okay, so that this factor is less than order. Okay. So in order to estimate P, you only need to estimate all these things. Okay. And it can be done by the following technical lemma. If you have F1, F2, F3 satisfying this Fermat functional equation of degree 6, then you have all this estimate, okay, with the capital R. Okay. So what you need to do is then you just put in all these things into the P. Okay. And finally, you will get P is bounded above by this expression. Okay. And because we know that our capital F is a Brody curve, and the order of it has to be less than or equal to 2. And so this P pipe is just basically you can choose it to be getting closer and closer to 2. So you will find out that again in this case, okay, so the P has to be constantly equal to 0. Okay, and therefore you get a trivial solution. So so the conclusion would be the following. So if A is unbounded, then F has to be trivial. Okay. So in other words, if F is a non-trivial Brody curve, then A is bounded, and therefore the order would be less than or equal to strictly less than 5/3. Okay. So this complete the first step, and then the second step and the first step would be basically the same. Again, using this Evan-Mankel's result. So eventually you will come to this point where you have the order of growth less than or equal to 1. So now I want to so I still have something like 10 minutes.
10 minutes.
10 minutes. Tell you one application of this result about Brody curve. So and also have some connection with other problems. So here is a so-called compact case of a Green-Fields conjecture, and you apply to this particular situation when you have this compact projective space Pn. Okay, so let D to be a non-singular hypersurface. in Pn. Okay, and assume the degree of it is greater than or equal to n plus 2. N is this number here. Okay. And then the conclusion would be any holomorphic map from CP into this D will lie in some proper algebraic subvariety of D. And I think this conjecture is still open. Now, if you take this D here to be the Fermat hypersurface, okay? So and then Mark Green actually proved the following result in 1975. Okay, so yeah. So M here would be a Fermat hypersurface of degree D inside a Pn. And if you assume the degree is greater than n squared minus 1, then the image of each holomorphic map from CP to M will lie in a linear subspace of a dimension at most n minus 1 over 2, take the integral. Okay. Now, if you take P to be 1, which is our situation, okay, and then the unsettled case for this Green-Griffith conjecture for Fermat surface would be D equal to 5 and also 6. Okay, because here you have D greater than or equal to n plus 2. Okay, so n in our case is equal to 3. Okay, so you have 5 here. Okay. So if you just consider entire solution of the functional equation, the only unsolved case is D equal to 6. Okay, and then we believe that so any solution should be achieved in that case. Okay. However, for D equal to 5, okay, so already we have one example by Gunderson and Toji, okay, which is a non-trivial example. But for that example, is actually you can check the image is lying inside a proper linear subspace of precisely this dimension. So for 5, I think it's even more difficult because basically you need to find all the solution to check whether this is true, or if you can find something different. Okay. Now, so finally, I want to tell you one approach that we are working on to solve the degree 6 case. Okay, it's related to nonlinear current. Okay, so let X to be a compact projective variety, okay, and take alpha to be a smooth one-one form. Okay, and then let omega to be any fixed Taylor form on X. Okay, and then we can define the nonlinear characteristic using this formula. Okay, for the holomorphic curve G from C to M. Sorry, this M should be X here. Okay. And then for this G, okay, we can construct something called the nonlinear current in the following way. Okay. So so this is our TRG omega. Omega is a fixed Taylor form. Okay, but then we also can consider this expression, similar expression, and then we take the quotient here. Okay, and so it will be denoted by this notation here. And McQuillan, he said you can choose some sequence, okay, so that these things actually converge in weak topology to a closed one-one current, and so given by this notation. Okay. And so this one-one current, positive closed one-one current, will be called the nonlinear current. Okay. There's something similar called alpha current, but I'm not going to define it here. Okay. And then there's a interesting result about this nonlinear current and also Brody curve. Okay. So it says the following. So you take a T to be a nonlinear current, on X. Okay. And then assume T charge on a compact subset K of X. Okay. So the conclusion is you can find a Brody curve which intersect K with non-zero area. Okay. So there's a similar result for alpha curve proven earlier. And then for positive closed curve, okay. So there's a well-known result by Yang-Tong Xiu, and actually he proved that for this kind of curve, you can have this representation. Okay, so you can write it as a sum of some other special curve, and those curves are associated with irreducible algebraic curve in our case. Okay, because we are considering a surface. Okay, and then there's also a subset K, which has a positive Random number on a set of dimensions here. So essentially, for this kind of a positive one curve, you have a representation or decomposition. Okay, but this is a general result. Okay, so if you just apply this general result, you don't know what this DI would be. Okay. Now, using our result, we can actually prove that this DI has to be those trivial curve that defined by the trivial source. So the linear curve associated with a holomorphic map into the degree 6 Fermat surface has this representation. Okay. So we are trying to use this to solve the degree 6 case. Okay, so I think I shall stop here.
Any questions?
So you had these solutions in the case of d equals to 5, and from what you were saying,
Yeah.
these are not known to be all solutions.
Yeah, just
In the case of d equals 2, you know all solutions, right? Is that the case? Or,
equal to 2. There's some other solution,
okay.
but it's not sort of if you want to confirm.
I mean, in the original question, right?
N, you mean N instead
Sorry,
of-
n equals to 2. Sorry, yeah. N equals n equals to 2. Not n.
There's some non-trivial solution.
There's some non-trivial solutions, but was this the case when you knew all non-trivial solutions, or?
No.
No.
All these examples are just
Okay.
very special example. No one knows how to.
For 2, 3, and 4, they get very confusing.
Okay.
But for this case, if you want to confirm this conjecture for Fermat surface, you also need to study the case when E is equal to 5.
Yeah, so can you highlight what goes wrong in your argument in D equals 5?
There are a number of cases that you really need to use the fact that it's 6.
Can you highlight one?
For example, you do sorry. This kind of thing.
Lemma 2?
Yeah, level 2. You need to use the fact is 6, degree 6.
So A is false when D is 5?
What?
So 2A is false when D is 5?
I don't know, but in the proof you need to use basically 6 is equal to 2 times 3. I think.
So so you're ruling out any Brody curves for n equals 6, but I guess the general.
Non-trivial Brody.
Yeah, non-trivial ones. So in general, do you think that there are any non-Brody, non-trivial non-Brody solutions?
Our conjecture is there's no.
Okay.
Yeah. And we are trying to use the last part, the linear current fix to do it. So hopefully we can finish. Yeah.
If you have instead of sum of three functions, if you have sum of k entire functions to the powers n, so you have two parameters.
Yeah.
So if n is big
Yeah.
and both, I want
There are
three.
already some estimation.
Yeah, so what is the critical relation between k and n when you stop to have solutions?
I don't remember that things. There's a paper by Walter Heyman. He actually has a nice.
But it's known.
Yeah, it's not.
Yes, what is the relation between k and n when there are no entire solutions?
No, when all these things is whenever you fix k, you fix the number of coordinate. Okay, and then when n sufficiently big, then there's no.
No, this I understand, but
Yeah.
if you allow both to go to infinity,
Both goes with infinity.
Yes.
I don't recall it. There's some inequality, but I don't recall it.
just what I'm curious, so what is
Yeah.
what is the relation, how one should go corresponding to the other?
I can check, but I cannot recall it.
Any more questions? All right, if not, let's thank Patrick again.